7, 8, 9, raspy and alive. I see you in everything. My vocabulary's limited, but I wanna tell it all to you. If I could.
The next big result that we're moving towards in this lecture is Theorem 13 in section 14.2 of Dummett and Foote, which is going to give us another way to understand when a finite extension K over F is a Galois extension. But I want to present this in a slightly different way, where I'm going to pull out one of the parts of Theorem 13 and prove it separately. So I'm calling this proposition 13 star. So the piece that I want to prove here is that if K over F is Galois, then every irreducible polynomial with coefficients in F, which has a root in K, is separable and has all of its roots in K. So as long as the polynomial has one root in K, it has all of its roots in K. It splits completely in K. Okay, so if every irreducible polynomial with coefficients in F that has a root in K is separable, that shows that K over F is separable. Why? What does it mean for an extension to be separable? That means that every alpha in K is separable over F. So any alpha in K is the root of its minimal polynomial over F. So that's an irreducible polynomial with coefficients in F that has a root in K. So we're proving that that polynomial is separable, so alpha is separable. Okay, let's do the proof. Suppose that K over F is Galois. Let's say that P of X in F bracket X is irreducible, and it has a root in K, so let's name that root. And suppose that alpha in K is a root of P of X. This extension is Galois. Remember in Dummett and Foote, when we define what it means for an extension to be Galois, we're defining what it means for a finite extension to be Galois. So this extension is finite. This Galois group is finite. So let's name the elements of this group. G is going to consist of the identity sigma 2, sigma 3 up through sigma n. That's Galois K over F. We'll just call that G. And what we're going to do is see where does alpha get sent by all of these elements of the Galois group. So we're going to consider this, I'll say multi-set because there might be repetition here. So alpha, sigma 2 of alpha, sigma 3 of alpha, up through sigma n of alpha. So there might be repetition here, but really all I want to keep track of are the distinct elements that arise here. So maybe there's some repetition. If you see repeats, throw them out and take alpha, alpha 2 up through alpha r to be the distinct elements in this multi-set star. Okay, so what are we going to do? Our goal, remember, we want to prove that P of X is separable, and we want to prove that all of the roots of P of X are in K. So what we want to prove is not just that they're somewhere in K, but that P of X is separable and all of its roots are in this set of elements, alpha, alpha 2 up through alpha r. All right, and what is the idea that we're going to use to show that this is true? We'll take another polynomial, f of x, that'll be the polynomial whose roots are exactly alpha, alpha 2 up through alpha r. So monic polynomial, x minus alpha times x minus alpha 2 times x minus alpha r. So these alphas are in K. So it's clear that this polynomial is in K bracket X. But what we're going to prove is that this polynomial is actually in F bracket X. So that's something we have to prove. And then we're going to prove that P of X divides this polynomial. All right, so this is the big piece of the proof. Why is this enough? So f of x has distinct roots in K. So if P of x divides f of x, then P of x can't have a repeated root because then f of x would have to have a repeated root. So since f of x is separable, P of x is also separable. So if we show that P of x divides f of x, then we will have shown that P of x is separable. So what about the other part? Well, we want to show that all the roots of P of x are in this set alpha, alpha 2 up through alpha r. So what we can note is that if you take an element of the Galois group, that gives a permutation of the roots of P of x and k. So if you look at this collection of elements, alpha, sigma 2 alpha, sigma 3 alpha, sigma n alpha, where does sigma 2 send alpha? It sends alpha to another root of P of x. So what are the things in this set? Everything in this set, everything in this collection is a root of P of x in k. So I didn't quite have space to finish this piece of the argument here, so I'm going to pause and erase, and then I'll explain how this implies that all of the roots of P of x are in this set, and then we'll prove what we need here, that f of x is in f bracket x and that P of x divides f of x. We're in the process of explaining why proving this set of statements about this polynomial f of x is enough to complete the proof of this proposition. So we've seen that this set, which has alpha, sigma 2 of alpha up through sigma n of alpha, consists of roots of P of x in k. Then we did this thing where we went from this collection to the distinct elements in this collection, which is alpha, alpha 2 up through alpha r. So what are the distinct elements in this collection? Well, this collection has a bunch of roots of P of x. So if you take the distinct elements, you contain each root of P of x at most once. So maybe you have some root of P of x that occurs like 10 times in here. When you take the distinct elements, you would get that root once. But maybe you have some root of P of x that doesn't occur in this collection at all. When you take the distinct elements, it still doesn't occur. So in this set, alpha, alpha 2 up through alpha r, you contain each root of P of x at most once, either 1 or 0 times. So what does that mean? That means that f of x divides P of x in k bracket x. Because if we look at the roots of f of x, they are contained in the set of roots of P of x. So if we've shown that P of x divides f of x, here we just explained why f of x divides P of x. So if we have division each way, these polynomials must actually be equal. So what would that mean? That would mean that all of the roots of P of x lie in k, because it's very clear that all of the roots of f of x lie in k. That these roots of P of x in k, they don't just lie in k, but they lie in this set that we wrote down, alpha, sigma 2 of alpha, up through sigma n of alpha. Okay, so what do we have to do for the rest of this proof? We have to show that this polynomial, f of x, actually has coefficients in f bracket x, and we have to show that P of x divides f of x. So let's do this first part. And the idea is going to be that we want to show that f of x has coefficients in the field f by showing that the coefficients of f of x are fixed by every element of G. So what does that mean? That means that the coefficients lie in the fixed field of G. So they lie in the set of things in K that are fixed by every element of G. But we know what the fixed field of G is. It's F. So if we can show that the coefficients of f of x are fixed by every element of G, then we'll know that f of x is in f bracket x. Okay, so I'm going to pause and erase, and I'll finish the proof by showing that the coefficients are fixed by every element of this Galois group G, and then by showing that P of x divides f of x. Let's finish the proof first by showing that the coefficients of f of x are fixed by every element of G. So let's name an element tau in G. And if you take all the elements in G, 1, sigma 2 up through sigma n, and you apply tau to each of them, then we're just multiplying the elements of a group by a fixed group element. We get a permutation of the group elements. So if you take tau, tau sigma 2 up through tau sigma n, we have the same collection as 1 sigma 2 up through sigma n. So we applied each element of G to alpha and got this collection, alpha, sigma 2 alpha, up through sigma n alpha. And if we apply tau, tau sigma 2 up through tau sigma n to alpha, we'll get tau alpha, tau sigma 2 alpha, tau sigma n alpha. That'll be the same collection, just permuted in some way. So if you take the distinct elements of this first collection, alpha, sigma 2 alpha, up through sigma n alpha, you take the distinct elements, the set of distinct elements in this collection, tau alpha, tau sigma 2 alpha, tau sigma n alpha, that's the same. And okay, if you have the same collection of distinct elements, you can't have like a repeated element and then have tau send that same element to 2 different places. So it must be the case that if you take this set alpha, alpha 2 up through alpha r, and you apply tau to each one of those elements, you get the same set, just permuted. Tau alpha 2 up through tau alpha r is the same as alpha, alpha 2 up through alpha r. And if you now think about what the coefficients of f of x are, when you just multiply out all those linear factors, you'll see that this means that the coefficients are fixed by tau. Okay, so tau is an arbitrary element of G. So the coefficients of f of x are fixed by every element in G. So they're in the fixed field of G, which is f. So f of x is in f bracket x. Okay, so there's one thing left to do, which is to see that p of x divides f of x. Well, what do we know about p of x? It's an irreducible polynomial, and it has alpha as a root. So it is the minimal polynomial of alpha over x. So we know that the minimal polynomial of alpha over x, sorry, alpha over f. So we know that the minimal polynomial of alpha over f divides any polynomial in f bracket x that has alpha as a root. In particular, this polynomial f of x is a polynomial in f bracket x, and it has alpha as a root. So we conclude that p of x divides f of x. We've already seen above that f of x divides p of x, so they are equal. And this completes the proof of this result.